Hi guys. So today we're going to be looking at energy production calculations. Now, the one thing that I want to make sure that we get today is that all of these calculations are going to be using things that we already know. All right, so there's not going to be anything new here. It's with the exception of the wind formula, but you got that in your reading last night. But for the most part, these things are going to be applying the ideas of mechanics. It's going to be applying the ideas of thermal physics, right? It's going to be using things that we already know to be able to answer a question. All right, so let's go ahead and go straight into it, and I want you to see what we're talking about. Now, so here we go. Energy production calculations with wind, water, fossil fuels, and fission. Oh my! Here we go. So the first one we got here, I do want to just talk, really quick about wind power, just because this is the one formula that is new, the one formula that we get that's new that we haven't seen before. You did see it in your reading last night, so hopefully you were able to get a basic idea of it. But I do want to just take really 1 minute really quick to cover it. Okay, so the important thing here is that the energy is coming from the air, right? The particles of the air, they have kinetic energy because they're flowing on by. Those particles are bumping into the blades of the windmill. The windmill is then spinning around, which now gives us rotational energy. That rotational energy, of course, then turns some type of generator, which is a wire inside a magnetic field that, as you've learned with your other types of fuel, that creates the electricity that we can then use in other situations. All right, so what's going to be important? Obviously, the kinetic energy of the wind is going to be important, and that's one of the things that we start with. Now, there is a derivation to get from here to the final question. I'm not going through that derivation now. You want to go through the derivation, you can look in your Tsokos book or your Oxford book, or I'm sure if you have some other book that you want to look at, it's probably in there. They usually talk through this derivation. But you can just kind of picture in your head, you've got these particles rushing through, so the energy of that kinetic of that wind is what's important. The second thing is how much wind goes through. Now, the amount of wind that goes through, you can talk about volume. You can talk about, if the wind's moving faster, then more particles are going to go through. You can think about it in any of those ways. But in the end, what's going to end up happening is that the speed is going to be extra important, not just because of the kinetic energy, but because if the wind's flowing faster, then you're going to get more wind through there. All right. So in the end, we do end up with this formula down here on the bottom right, which you can see. The 1/2 a rho v cubed. The area is the area that's swept out by the blades. Now, generally speaking, your blades are going to look something like this. And as they spin around, they cover this area, which is a circle. Now, that circle, usually the area is going to be pi r squared, where r is the length of one of those blades in the windmill. All right. The rho is the density of the air, as you can see in this right here. And then last of all, of course, is the wind speed, which, as I mentioned, you've got the kinetic energy, which is v squared. But again, the speed of the wind is going to be extra important because it also means more particles coming through, which means more energy. All right, so that's the idea of the wind power equation. The other thing I do want to mention, just because I can and because you're stuck watching me right now, is the idea that not all of the kinetic energy, when we use this formula, the 1/2 a rho v squared, that's an ideal energy, right? That's the maximum possible amount of energy that we can get from, power, I'm talking about energy per time, power that we can get from the wind. The reason being is that if we took all of the energy out of the wind, what would happen? Well, if we took all of that kinetic energy out, then it wouldn't have any kinetic energy left. Therefore, the air would stop. And if the air stopped there, then no more air would be able to come through. And so therefore, our windmill wouldn't be able to spin anymore. So ideally, we don't want to take all the wind out, strangely enough, all the energy out, all the power out, because of exactly that. We want the air to be able to continue on past. So it has to have a velocity after the windmill as well, which means we don't actually take out all the kinetic energy. But that's good because then more energy, more we can flow. All right. So hopefully that kind of makes sense. Let's move on and actually do some of these problems now. Okay. Here we go. The first one is, look at this, a wind turbine question. All right. A wind turbine produces a power P at a particular wind speed. If the efficiency of the wind turbine remains constant, estimate the power produced by the turbine. All right. So if the speed doubles is the first question. So we're going to look back. I'm actually going to get our equation right there so that we can use that. So the original equation was 1/2 a rho v squared. Okay, so if we start with that, what would happen if the wind speed right here, sorry, that should not be a square, that should be a cubed. What would happen if the wind speed doubles? Well, that would then give us 1/2 a rho 2v cubed. Now, if I cube both the 2 and the v, then I get 1/2 a rho 8v cubed. And if you'll remember, 1/2 a rho v cubed was p. So 1/2 a rho v cubed is p, so I'm left with 8p, which means that if the wind speed doubles, then the power is 8 times what it was before. All right. What if the radius of the blade length halves? Okay, well, that's going to come in to this part right here. Again, we're going to start with 1/2 a rho v cubed. The a, remember, is the area that the windmill covers. Okay, that circular area covered by the blades. Okay, so I'm going to change that into 1/2, and I talked about this in the previous part, pi r squared, because r is the length of one of those blades, and then rho v cubed, and then we're going to half the length of that blade. So this is going to become 1/2 pi 1/2 r squared rho v cubed. So I'm halving that r for this second situation. Recognize that in the first one, this was the first situation, this was the second situation. This is the first situation, this is the first situation. Now this is my new situation, right, where I've halved the radius. So when I go through that process, I end up getting 1/2 pi, distribute the squared, 1/4 r squared rho v cubed. Now you'll notice that compared to the first situation, I've got the 1/2, the pi, the r squared, the rho, and the v cubed. So all of those things together give me the original power, right? And so what I'm left with is 1/4 times the original power. Or in other words, if the radii of the length halves, then my power is going to be 1/4 of what it used to be. All right, so that's how you work that specific type of question. All right, let's delete that and move on to another type of question. All right, we're going to do another wind power one just because we're on the topic. A wind turbine with blades of length 25 meters is situated in a region where the average wind speed is 11 meters per second. And calculate the maximum possible output of the wind turbine if the density of air is 1.3 kilograms per meter cubed. All right, so we know that power is equal to 1/2 a rho v cubed. We have actually all the information that we need there, so we'll go ahead and put those in. It doesn't give us the area covered, but it does give us the length of the blades, so we're going to go pi r, which is 25 squared, so that's my a there. And then the rho, the density, is 1.3 kilogram per meter cubed. It's all in SI, so that's nice for us. That is a 1.3. And then we'll go times the velocity, which is 11, again in SI already, meters per second. And that will be cubed. And then we should be able to work that out and get a final answer. So I'm going to work that out. You work it out. Make sure you get the same thing as me. Here we go. All right, so that's what I got. I got 1.70 times 10 to the 6 watts. Yep, it was pretty close to that. I rounded it to 3 sig figs. That's what you should do as well, is round it to 3 sig figs and be done with it. The information given to us is in 2 sig figs, so you'd probably be okay if you just put the 1.7 times 10 to the 6 watts as far as the IB exam is concerned. So that should be fine, just like that. All right, the next question is outline why your estimate will be the maximum possible output of the turbine. If you want to answer that question, rewind the video about 3 or 4 minutes and you'll get the explanation there. Okay, so try to answer it. Double check your answer. Remember, it has to do with the fact that the wind is not going to stop. The wind has to continue passing through, which means you can't actually get all of the kinetic energy of the wind turned into the useful power. Okay, all right. let's move on. We're doing good. Here we go. Next up. Water from a pump storage system falls through a vertical distance of 260 meters to a turbine at a rate of 600 kilograms per second. The density of water is 1,000 kilograms per meter cubed. The overall efficiency of the system is 65%. Therefore, calculate the power output of the system. All right, so this should be a pretty straightforward question given what we already know. We have water that's at a certain height. It's falling through a vertical distance. The horizontal doesn't matter, right? Because the force of gravity is pulling down. So that's where we're gaining our energy from, is from that change in potential energy. So the water falls down. We have a specific rate that then allows us to answer the question that we're looking for. Now, here's the key, is that it's not giving this information in ways that we're used to, right? So the information that we've got is that we have a vertical distance, or the change in height is going to be 260 meters, okay? The water is going down at a rate, so this is what we call the mass flow rate, is 600 kilograms per second. And it says the density of the water, so that's rho, density of the water is 1,000 kilograms per meter cubed, okay? We'll worry about the efficiency later. The efficiency is 65%, which we can use at the end. Now, we know that we're dealing with a case of potential energy, right? We're looking at how much potential energy is being lost by the water, which then turns into the kinetic energy of the water, which ideally we're going to take all of that kinetic energy. Again, just like with the windmill, the water can't actually stop. The water's got to keep flowing, which is part of that 65% there. So let's find out how much energy, right? Or really we want power, but we know, for example, that the change in energy is going to be equal to mg times the change in height. This is conservation, right? Energy conservation. We're hoping that all of that energy, the potential energy that's lost, is going to turn into the energy that we get. Okay, so how much energy is it possible for us to get? Well, it's that change in potential. So that's what we're going to look at right now, the mgh. So how much mass is coming? Well, it's 600 kilograms per second. Right? Now, 600 kilograms per second is fine, because actually, if I have per second, that then means that this energy, so what I'm going to do is just actually really quick, I'm going to say, well, what happens if I divide this by time? Because that's really what I want, right? It's asking for power. So energy over time, and I've got mass over time right here. So the change in energy over time, or the maximum possible power, is equal to mass over time, which was 600 kilograms per second, times gravity, 9.81, times the change in the height, which was 260 meters. Go ahead and calculate that. I will too, and we'll see if we get the same thing. All right, so this is what I got. I got 1.5 times 10 to the 6 watts, so that's the amount of power that's being generated by that water falling down. Okay, the other thing is that we want to look at the total power output, which means we now have to include that 65% down here. So we're going to multiply the ideal power output by the efficiency, and that's going to give us about 9.9 times 10 to the 5th watts, which is going to be our total power output and the answer that we're looking for. Okay, it did give us some extra information there, right? It said density of water is 1,000 kilograms per meter cubed. Not important in this specific situation. It's possible that this question maybe has other parts. If we wanted to find the speed of the water or something like that, we could get that given the density of the water. We could turn the kilograms into volume or whatever else. Okay, so awesome. There we go. We got our answer. And again, I want you to notice that this question was answered by using information that we already knew, right? Using energy conservation, using that idea of power, efficiency, right? We didn't need anything new in order to be able to answer this question. All right? Okay, here's our next one, fossil power. And I think we've done one like this before, but I want to make sure that we talk through it and have an idea of how to work through it. Again, having just the information that we already have. Okay, so a fossil fuel power station has an efficiency of 25%. So I'm going to write it down as we go. And generates 1,200 megawatts of useful electric power. So the power that we get is 1,200 megawatts. The specific energy of the fossil fuel is 52 megajoules per kilogram. So 52 megajoules per kilogram. All right. Calculate the mass of fuel consumed each second. Okay. So here what we're going to do is, this is basically just a conversion, right? So this is the power out, which is 1,200. And actually I'm going to turn that into times 10 to the 6 because that's what the mega is. And this is watts, okay? And we are going to turn this into, eventually, hopefully we want to turn it into mass of fuel per second, okay? So watts, of course, is joules per second. So I'm going to go ahead and change that. Okay. Now, first, I need to, right now I know how much power is coming out, but I need to find out how much needs to be burned. So how much actually is going into it. So I'm going to do the efficiency thing, right? And so I get, I'm going to need to take that number, that 1,200 times 10 to the 6th, and if I multiply by 25%, it's going to get smaller. This is actually the output, and so I need to divide by 25% to give me how much I actually started with. Okay, so I'm going to actually do that efficiency here, and I'm going to turn it into, if I divide by 0.25, that's going to give me 4,800 times 10 to the 6th joules per second. Okay. Now I need to turn that into mass, right? And it did give me the specific energy. Specific energy is megajoules per kilogram. So I want my joules here to turn into kilograms, and I want the joules to cancel out. So if I put the joules down here on the bottom, then the joules are going to eventually cancel out. So what I see here is 52 megajoules, or 52 times 10 to the 6th joules, is 1 kilogram. It's just a conversion, right? That then means that the joules are going to be able to cancel out. The kilograms are going to be left on the top, and look at this, I'm going to have seconds down on the bottom. Okay, so I'm just going to multiply the things on the top, 4,800 times 10 to the 6th times 1, and then I'm going to divide by the thing on the bottom, 52 times 10 to the 6th, and that will give me the answer that I'm looking for in kilograms per second. So I'm going to go ahead and do that. You do it as well. Let's see if we get the same answer. All right, this is what I got. I got 92.3 kilograms per second. Now, that's pretty fast. That's a lot of mass, right? That's like my full body weight every second. I know that's half my body weight, but somewhere around there. Anyway, you get... No, that's my body weight. Just kidding. Sorry, getting mixed up with the whole kilogram pound thing. Yeah, I don't want to do that. So yeah, about my body weight every second. Now what that means is, as you see in the note here, that's about one full rail car. If you've ever seen a train with those big, huge rail cars with coal, one of those every 2 minutes. That's how much coal you need to burn in order to get this much energy, which is for a small, medium-sized town. All right, so recognize how much coal is needed for this process of a coal power plant. Okay, all right, I think that's good. Let's take that off, and we will move to the next one.